Hello, my name is Mr. Asprey and this is 2022 EDEXCEL A-Level Further Maths Core Pure Mathematics Paper 1. I'm very excited about this paper. It's the first A-Level Further Maths that I've done on this channel, and hopefully there'll be much more. So if you do appreciate it and you do find it useful, then please do like the video and also subscribe for more A-Level Further Maths content coming very soon. Okay, let's get into the paper. Okay, question 1. We are told that we have a complex root of this following cubic equation. It says write down the other complex root. Well, the other complex root will be its conjugate, which is 2 plus 3i. So nice easy starter to get us warmed up. And then part B, it says hence solve completely. Now there are a few ways of doing this. I think the quickest and most efficient way is to use our roots of polynomials rule, and that is that the sum of the roots, so the sum of all the alphas, is equal to minus b over a. In this case we don't have a z squared term, so therefore b is 0. So the sum of the roots is equal to 0 over a, which is 0. And the sum of the roots will be 2 minus 3i is the first one, plus 2 plus 3i, plus the third root, let's call it gamma. And that's going to equal 0. So the minus 3i and the plus 3i will cancel, so we get 4. So therefore the third root is equal to minus 4. Okay, the second part of B says determine the value of a, where a is the z coefficient, which is unknown. We can use the factor theorem for this, seeing as we know that we have a root of minus 4. Then f of minus 4 will equal 0. So substituting into the function minus 4 cubed is minus 64, plus az, where z is minus 4, so minus 4a, plus 52 is equal to 0 by the factor theorem. So this tells us that minus 12 minus 4a equals 0. So we can say that a must equal minus 3. Finally, it says show all the roots of the equation on an argand diagram. So I'll start by drawing my argand diagram like so. Label this the imaginary axis, this the real axis. And I have one root at minus 4, which is a real root, so that would be here. Label that minus 4. And then my other two roots are 2 plus 3i, so 2 along and 3 up. So let's label that 2 plus 3i. And then its congregate pair, which is down here, this will be 2 minus 3i. So that would be 2 on the real, that would be 3 up there, and that would be minus 3 there. And we're done. Question number 2. It says determine the values of x for which 64 cos to the 4 minus 64 cos squared minus 9 is equal to 0. Okay, so this is a form of quadratic in that we have cos to the 0, cos to the 2, cos to the 4. So therefore we can say let y equal cos squared x, and then we'll have 64y squared minus 64y minus 9 equals 0. We can solve that quadratic by using our calculator. I think it's probably the most efficient way of doing it, seeing as it's going to be quite a tricky one to factorise. So we'll go to polynomial solver, degree 2, and that's 64, minus 64, and minus 9. And we get 9 over 8. So we say that y is equal to 9 over 8. And we also have minus an eighth. So we say y is equal to minus an eighth. These are cosh squareds. So we can write this. And this one here is a negative, and you can't have a square equal to a negative. So this one has no solutions. Making sure that I show that nice and clearly. Whereas this one gives me that cosh x is equal to plus or minus, what's the square root of that? So that would be 3. Let's just use our calculator for this. The square root of 9 over 8, which will give us 3 root 2 over 4. Perfect. And we know that the cosh graph looks like this, so therefore it can't take negative values. So the only solution here, we can say that, sorry, minus 3 root 2 over 4 is not a solution, it must be rejected. So we have that cosh x is equal to positive 3 root 2 over 4. And from our formula booklet, we know that arc cosh of x is equal to ln of x plus the square root of x squared minus 1. So now we can say that x is equal to ln of 3 root 2 over 4 plus the square root of 3 root 2 over 4 squared minus 1. Okay, now we need to simplify this. So I'm going to go to our calculator, and I'm going to start here. So I'm going to square this, which gives me 9 over 8. And then if I minus 1, it gives me 1 over 8. So I'll just write that line of working. So I'll say that x is equal to ln of 3 root 2 over 4 plus the square root of 1 over 8. And then I will square root that and get root 2 over 4. So I've got a root 2 over 4 plus 3/4 root 2 over 4. So that just gives me 1 whole root 2. And this is the same as what form they want it in. They want it in just a ln 2. So this is the same as 2 to the power of a half using log rules. Not even using log rules, so the square root of 2 is just 2 to the half. And then the half can come down using log rules. And we are done. Okay, next question is a differential equation, and it is a first order one, so it looks like we're going to have to solve this using the integrating factor. First step would be to isolate the dy by dx, so I'll do that by dividing everything through by cos x. So this gives me dy by dx plus, and I divide sine by cos, I get tan, so that would be y tan x. And then over here I'm going to get e to the 2x and just a single cos x. Okay, great. Now using integrating factor, the integrating factor will be whatever is multiplied by the y in this case, so tan x. So it'll be e to the integral of tan x dx. Like that. The integral of tan x from our formula booklet is ln sec x. Now I've got e to the ln, so those two will cancel, so it means that the integrating factor is sec x. Okay, so what's the next step? Is to multiply this differential equation by the integrating factor. So that gives me dy by dx sec x plus y tan x sec x is equal to e to the 2x, and a cos x times by sec x is just going to be 1, because sec is 1 over cos, so times by cos is just going to give you 1. Okay, now I can write this as a product, and the product will always be the variable y, so the one on top of the differential, so dy by dx, it will always be the top one, y, multiplied by the integrating factor. And that will equal e to the 2x. Of course, we could check to make sure that's correct. If I take y and if I differentiate this product, y differentiates the dy by dx multiplied by sec x. And then here, the next one, we will differentiate sec x to get sec tan, and then keep the y the same, and that will give us our product. Okay, next step is to integrate both sides. Integrating and differentiating are inverse operations, so they will cancel, and we'll just get y sec x, and the integral of e to the 2x is 1/2 e to the 2x, and we have to remember plus c. We want our answer in the form y is equal to f of x, so we write y is equal to, now I'm dividing here by sec x, but dividing by sec is the same as timesing by cos, because they're reciprocals of one another. So I can write 1/2 e to the 2x cos x plus c cos x. Okay, next part says, given that y equals 3 and x equals 0, determine the smallest positive value of x for which y equals 0. Right, so we can use these conditions here to work out our c value. So subbing in y equals 0, sorry, y equals 3, x equals 0. This is going to give me 3 is equal to e to the 0 is 1, cos of 0 is 1, so that's all times by 1/2, it's going to give me 1/2, plus, and again cos of 0 is 1, so that's just c, so c is equal to 5/2. So our particular solution is as follows, and what I can do is I can factorize out a cos x like this, and we're told in the question that we want to work out the smallest positive value for x for which y equals 0. So we're going to set this equal to 0. Now we won't be able to make this bracket 0 because e to the x can never be negative. So the only way we're going to make this function here equal to 0 is if cos x equals 0. And cos x equals 0 at pi/2. And that's the smallest positive value where cos x equals 0. And we're done. Okay, question 4, we need to use method of differences to prove this summation here. I'm going to start by using our ln rules to split this up. So we can say that the summation of n from 2 to n of ln of r plus 1 over r minus 1 is the same as the summation using ln rules of ln of r plus 1 minus ln of r minus 1. Okay, great. Now let's just have a look to see how these series develops. So we'll start with r equals 2, and we'll get ln of 3 in the first slot, and here we will have minus ln of 1, and then we will keep going. So we will try r equals 3, and this will give me ln of 4, and it will give me minus ln of 2. R equals 4, ln of 5 minus ln of 3. 5 will give me ln of 6 minus ln of 4. And then we're going to go all the way down to, let's try n minus 2. Why not? And then add on 1 will give me ln of n minus 1 minus ln of n minus 3, and then we'll get ln of n minus ln of n minus 2, and then finally we'll have ln of n plus 1 and ln of n minus 1. Okay, it might be a bit over the top to do all of these, but I like to do it, it's fun, and we get to then see the cancellations. So this will cancel with this, 4 will cancel with minus 4, and we're going to get this type cancellation shape, so that will go down to there. This will cancel with this. So on this side, these will cancel as well, with ones in between. Dot 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 dot. And following this pattern, it means that we're going to get this one cancelling with that one. So all of these on that side will cancel with ones above, like that. So we're left with the summation n r equals 2 of ln r plus 1 over r minus 1 will equal, first off, this is 0, so that will go. We've got these positive ones down here, so ln of n plus ln of n plus 1, and we've got one negative here, minus ln of 2. So we can rewrite this using our log rules. We've got these two positives, so they will go on the top, they're multiplied, so n plus 1. This is negative, so that will go on the bottom, 2. Perfect. Okay, next we're going to say hence, which means we're going to need to use the formula we've just created above to find the exact value of between 51 and 100 of this ln to the power of 35. Okay, so we're going to write ln, the summation from, it was 51 of ln. Now we can rewrite this r plus 1 over r minus 1 to 35. So we can rewrite this as, first of all, we can bring the 35 down as it's a power, and it can come out of the brackets because it's multiplied by a constant. So we have this. And then if we're summing from 51 to 100, but we know the sum from 2 to n, then I could write this as 35, the summation of 100 from 2 minus the summation of 50 from 2. So let's just double check that makes sense. This is going to give me all the numbers from 2 to 100, and then I'm going to take away all the numbers from 2 to 50, so that will leave me with just the numbers between 51 and 100. And we know what these values are, these summations, because we've already shown that if you want to go up to n from 2, then all you need to do is just sub in n into this formula here. So I can write that this is equal to 35, and we are going 100, and the formula was n plus 1 over 2. So it's ln of 100 multiplied by 101 over 2 minus, now we're going up to 50, so it's ln of 50 times 51 over 2. Okay, we've got these ln rules here. We can combine them to get 35 lots of ln. Well, first off, let's work out what is 100 times 101 divided by 2. So it's 5050. And then we've got 50 times 51 divided by 2, and that will be all over because we're combining these lns. We've got a minus sign in between, so we're going to be dividing. So 1275, and they want their answer in a ln b over c, where a, b and c are integers to be determined. So I think we're done. I mean, we could do a little simplifying here because I'm sure there's a factor which we could take out. 202 over 51, great. So 35 ln 202 over 51. Sounds good to me. Question 5, we've got to show that this matrix is non-singular for all values of A. So we're going to need to work out the determinant. And we would do that by first selecting the top left element, crossing it out like that. So we're doing A multiplied by the determinant of 30A2. And then the middle one we always subtract. We select this element here. So it's 2 multiplied by 2042. And then we take minus 3. So plus minus 3. And the determinant will be 2, 3, 4, and A. This is going to give us 6 and 0, so 6A. Give us 4 and 0, so minus 2 times 4 is 8. And 2A minus 12 times minus 3, so 2A minus 12. So expanding out, 6A minus 8 minus 6A plus 36. Cancel, cancel, 28. That's not 0, so therefore it's non-singular. Okay, great. Let's do part B over here because I'm going to need to look at that matrix whilst I do it. Because to work out the inverse, you'll need to take the matrix of minors, which takes a long, long time. So, let's just draw a big matrix like that, and I'm going to do the top left element first, so across out the column and the row, and then I do the determinant of what's left, so that is 6. Let's do the top middle, and that is 4. And then this one is 2A minus 12. And then we're going to go to the middle row. So we're going to get 4 minus 3A is 4 plus 3A. Then moving along, we're going to get 2A minus 12, so that's 2a plus 12. And then over here, we're going to get a squared minus 8. And then let's do the bottom row. So we're going to get 2, no, that's 0, minus 9 is 9. We're going to get a0, so that's 0, minus 6 is just 6. And then lastly, 3a minus 4. Okay, next step is to transpose the matrix. So everything down this diagonal stays the same. And then these two are going to swap over, and also their signs will change. So I'll have minus 6 here, and I will have 8 minus a squared. And then we'll do the same for these two, swap these two over, and their signs will change. So that's minus 4 here, and that is minus 4 minus 3a. And then finally, these two corners swap over, but their signs don't change. So we get 9 up here, and we get 2a minus 12. And the final thing, not sure why I left it to last, but we need to multiply it by the determinant, which is 1 over 28. So multiply it by 1 over the determinant, sorry. And there we go. There we have it. Partial fractions. Lovely. So let me write that this is equal to f of x, and then I can say that f of x is equal to a over the linear factor plus bx plus c over the quadratic factor. Okay, then what I can do is I can multiply through by x plus 1, x squared plus 4. And this will give me 2x squared plus 3x plus 6 is equal to a lots of x squared plus 4 plus bx plus c times x plus 1. Okay, great. The first thing I'm going to do is I'm going to let x equal minus 1. And that will give me 1 times 2 is 2, minus 3 is minus 1, plus 6 is 5. So I get 5 there is equal to minus 1 squared is 1, plus 4 is 5, so 5a. And of course these brackets here will cancel because x plus 1 will give you 0. So that tells me that a is equal to 1. Okay, great. Now what we can do is we can set x equal to 0. This gives me 6. This gives me 4 lots of a, which is just 4. This gives me c multiplied by 1, because that will be 0 and that will be 0, so just be c and 1 in each bracket, so just c, so therefore c will equal 2. And then finally you can pick just any value of x to find the final term. I'm going to go x equals 1 because it's just the easiest to sub in, and that's going to give me 2 plus 3 is 5 plus 6 is 11. I'm going to get 5a, so that's just 5. I'm going to get b plus 2, so b plus 2 multiplied by 2. So that's going to give me 11 is equal to 5 plus 2b plus 4. And this is going to tell me that b is equal to 9 minus 11 is 2, so b is equal to 1. So I can then write that f of x is equal to a is 1, so 1 over x plus 1, and b is 1, so just x plus 2 over x squared plus 4. And we've expressed it as partial fractions. Okay, part B is to integrate that now between 2 and 0. Okay, so part B is to integrate between 2 and 0 the function, which I'll express as partial fractions, so we can integrate it like so. With respect to x. Now the trick here is to split this one up because we can't integrate it directly in this form. So what I'm going to do is I'm going to write it as the integral of x over x squared plus 4. So we can integrate that using the Lund rule, plus 2 over x squared plus 4, and we can integrate that using the arctan rule. Okay, so the first one, if we look at the denominator, its derivative is 1, so we can integrate that directly using Lund's. We can say that is Lund of x plus 1, the denominator. Here, if we look at the derivative of this, it's 2x. So ideally, I would want a 2x on the top, which means if I was integrating that, I would take a half out. So the half would cancel with the 2. And now I can use the Lund rule directly. So it will be a half of Lund of the denominator, x squared plus 4. And we know from our formula booklet that the integral of 1 over a squared plus x squared is equal to 1 over a arctan of x over a. So in this instance we have, we're plussing on 4 to the x squared. So the a is a 2 squared, or sorry, a is 2, which means this is a 2, which means this is a 2. And then we have 2 on top, so we're actually timesing it by 2, which I can take out of the integral like that. So we're going to be timesing it by 2. So 2 times a half is just 1, so it's just arctan of x over 2. So plus arctan of x over 2. And that is between 2 and 0. Okay, subbing in our limits now. When we sub in 2, we're going to get Lund of 3 plus 1/2 of Lund of 8. And I'm going to get arctan of 1. And then I'm going to subtract the 0 limit. So that's going to give me Lund of 1, which we know is 0, so I'll leave that one out. And I'm going to get a half Lund of 4. And then I'm going to get arctan of 0, which again we know is 0, so I'll leave that one out. Okay, now I've got to write it as a single logarithm, I believe. Plus a value of pi in terms of, and logarithm in terms of root 2. Okay, so we've got Lund of 3. The half can come up here. And that will be Lund of the square root of 8, which is 2 root 2. Arctan of 1 is pi over 4. Minus, the half can come up, so square root of 4 is 2. So minus Lund of 2. Now, when we're trying to write Lunds together, I look at the positive Lunds. And that means on the top line it will be 3 times 2 root 2. And then we've got the negative Lund here, so that means you're going to go on the bottom. Like that. Plus pi over 4. That 2 will cancel with that 2 on the bottom. So we're left with ln of 3 root 2 and then plus pi over 4. And we're done. Okay, question 7. We need to show that z multiplied by its conjugate pair is a real number. So we will just do the a plus bi multiplied by a minus bi is equal to a squared plus abi minus abi and then minus b squared I squared. So we're going to get these two cancelling, and of course I squared is minus 1, so times by the negative there will be a positive, so we have a squared plus b squared, which is real. Okay, great. Right, next part is a bit more tricky. There's lots of different ways of doing this. I'm just going to show you what I think is the most efficient way. So first off, we know that that's equal to 18. We've also shown that's equal to a squared plus b squared. So we can say that a squared plus b squared is equal to 18. Okay, that's our first equation formed. Now let's find another equation by using the second bit of information. So that tells us that we need to do a plus bi over a minus bi. And I want to rationalize that denominator to make it easier to work with. So I'm going to multiply it by a plus bi on top and a plus bi on the bottom. This is going to give me, on the top, I'm going to get a squared. I'm going to get 2 lots of abi, and I'm also going to get b squared times by I squared, so that's minus b squared. And on the bottom, I'm going to get, well, I've already done that multiplication already. That tells me that I get a squared plus b squared. Okay, and we're also told that this is equal to 7 over 9 plus 4 root 2 over 9i. So now what we can do is we can equate coefficients. So we know that the real part is this. So I can write that a squared minus b squared, obviously over that denominator, a squared plus b squared is equal to 7 over 9. Or if you wanted to, you could equate the imaginary parts by saying that 2abi over a squared plus b squared is equal to 4 root 2 over 9. But I'm just going to stick with this real part here. And I know that from equation number 1 that a squared plus b squared is equal to 18. So I can write that a squared minus b squared over 18 is equal to 7 over 9. Multiply both sides by 18 tells me that a squared minus b squared is equal to 14. So with these two equations, I can now solve for a and b. So adding them together is going to give me 2a is equal to 32. So I'm going to get 2a squared is equal to 32, which is going to give me a squared is equal to 16, which means that a can be plus or minus 4. And then subbing back into one of the equations, let's sub back into this equation here because I can see it, the second equation. I'm going to get, well, if a is plus or minus 4, a squared will be 16 regardless. And minus b squared is equal to 14. So b squared is equal to 2. So b is equal to plus or minus root 2. Okay, so we might think at this stage that we're done. We've got values for a and b. Looks like they're going to be 4 different complex numbers, because you've got plus or minus for a and plus or minus for b. But we're not quite done, because we need to make sure that it also satisfies the imaginary part as well. So we've shown that those two solutions for a and b satisfy the real part. Let's check to make sure it satisfies the imaginary as well. So we know that that denominator is 18 from previous. So multiplying through by 18, or in fact what we can do is we can divide through by 2 first to get 1 and to get 9, and then both sides have denominator of 9, so they can cancel. So we get AB, also getting rid of the i's, we don't need to focus on the coefficient, is equal to 4 root 2. Okay, so that does restrict. That means that we can only have a, if a is positive 4, then that implies that b needs to also be positive. Or if a was negative, then b would be negative. So those are the only two solutions. So we have z is equal to 4 plus root 2i, or z is equal to minus 4 minus root 2i. Right, we're going to use the Moivre's theorem here. We are told that we're given this, as we always are, and we're asked to show that 32 cos to the 6 is equal to blah 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 blah. Okay. So let me get some space down here, and we'll start by writing that z plus 1 over z to the power of 6 is equal to 2 cos theta to the power of 6, which is equal to 64 cos to the power of 6 theta. I'll then need to expand this bracket here using the binomial. So we'll do 6c0, we will do z to the 6, 1 over z to the 0, plus 6c1, z to the 5, 1 over z to the 1, like this. I'll just speed this up. And we would get this, and then what I would do is I would evaluate each term. So 6c0 is just 1, so that's just going to give us a z to the 6, and then we're going to have 6, and then these z's are going to make 6 to the 4, and then we're going to get 15, and that will be z to the 2, and then plus 20, and that will be, the z's will completely cancel there, and then next we'll get another 15, and we're going to get z 1 over z squared, and then here we're going to get 6, and that's going to be 1 over z to the 4, and then finally we're just going to get plus 1 over z to the 6. Right, now we can collect z's and 1 over z's. So I could write that as z to the 6 plus 1 over z to the 6. And I could write that as 6 lots of z to the 4 plus 1 over z to the 4. Plus 15 lots of z squared plus 1 over z squared. And then finally plus 20. And we know that z plus 1 over z to the n is equal to 2 cos n theta. We can use this to say that this first term here is 2 cos 6 theta, and this is 2 cos 4 theta times 6, which is 12 cos 4 theta, and this is 2 cos 2 theta times 15, which is 30 cos 2 theta, and then plus 20, and all of this is equal to 64 cos to the power 6 theta. That's correct. The question asks us to find 32 cos to the power 6 theta, so we just divide this all through by 2, and we get as required. Okay, moving on to the next part of the question then. We have this paperweight with a flat base. We are going to be trying to work out the volume in between these points. It's all sort of given here. It needs to be rotated 180 degrees about the x-axis. And it says, given that the maximum height of the paperweight is 2 centimeters, work out the value of h. Well, we know that cos function goes to a maximum of 1, so this needs to go to a maximum of 2, so h must equal 2. And then it says use algebraic integration and the result in part A to determine the volume of the paperweight according to the model. Okay. So I need to find the area, and the formula is pi the integral of y squared dx, but because I'm only rotated 180 degrees, then it's half of this. Now y is the function which was 2 cos cubed x over 4. So if I square that, I get 4 cos to the 6 x over 4 dx. Now if I take the 4 outside of the bracket, that's going to give me 2 pi the integral of cos to the 6 x over 4, and we are going to use this identity here to substitute in. So I'm going to get a is equal to 2 pi divided by 32 the integral of cos to the 6 times x over 4 plus 6 lots of cos to the 4 times x over 4 plus 15 lots of cos to the 2 times x over 4 plus 10. Okay, let's integrate this then. Whoops, I've forgotten to put in the bounds. So it was between 4 and minus 4, if I am correct. Yep. Okay. Forgive me for this. So this is going to be pi over 16 between 4 and minus 4, and we're going to actually integrate now. So we'll put a square bracket. This is 3 over 2x, so cos will integrate to sine. We'll have 3 over 2x, and then we will divide by the derivative of that, so that will give me 2 over 3. And then next, this will be just sine x, so it'll be 6 sine x, and this one will be a half. So when I integrate, I will divide by a half, which is the same as timesing by 2, so that'll be 30 sine of x over 2, and then 10 will integrate to 10x. Close that up between 4 and minus 4. Okay, so a little shortcut we can take here is we can first off sub in 4, which would give me pi over 16 brackets 2/3 sine of 3 over 2 times 4, and then plus 6 lots of sine of 4 plus 30 lots of sine of 4 over 2 is 2 plus 40. And then what we can do is just double that, because we already know that from the diagram the function is symmetrical. So my area will just be 2 times 12.28. So I'll just times that by 2, and I'm going to get 24.56. Just to save time rather than subbing in minus 4. And again, it's because that sine, this curve here, is completely symmetrical. So we've just worked out the area between 4 and 0, and then I'm just going to double that rather than subbing in minus 4. Okay, first one, explain why this is an improper integral, and that's because we have an infinite limit. Next one, show that it is divergent. Well, we can write that the integral between infinity and 0 of cosh x dx is equal to the limit as t tends to infinity of the integral between t0 cosh x dx. And we can write that this is the same as, because we know that cosh is equal to 1/2 e to the x plus e to the minus x. Okay, so we can then take out a half, and we can integrate. So it's the limit as t tends to infinity of 1/2, and then when we integrate, or e to the x goes to e to the x, and this goes to minus e to the minus x between t and 0. We can sub in, so we're going to get 1/2 of e to the t minus e to the minus t minus e to the 0 minus e to the 0, which is going to give us 1/2 e to the t minus 1/2 e to the minus t. And then we can say that as t tends to infinity, e to the t will also tend to infinity, and e to the minus t will tend to 0, and therefore, because one of them there tends to infinity, we could say the integral the integral is divergent. Okay, next part. Given that the equation has real solutions, determine the range of possible values for P. Okay, so it's 4 sin is equal to P cosh. So 4 sin x is equal to P cosh x. Divide both sides by cosh, which is going to give me 4 tanth, and therefore that's going to equal P over 4. And the graph looks like this, where it's bounded between 1 and -1. So that means that P over 4 must be between -1 and 1. So therefore P is in between -4 and 4. And we are done for that question. Okay, final question is a differential equation question, and we have a pendulum that makes an angle theta with the downward vertical, and t is the time after it begins to move in seconds, and it says show that this is a particular solution to this. So I've got to just check to make sure that that solves this. So what I'll do is I'll take theta is equal to 1/12 t sine 3t. So I'll say theta is equal to 1/12 t sine 3t, and I'll have to differentiate that once, and that's going to, we're going to use product rule here. So I will keep the yellow the same, and then differentiate the blue, which will give me 3 cos 3t, and then I'll differentiate the yellow, which will give me a 12th, and I'll keep the blue the same. And I will simplify that to get 1/4 t cos 3t plus 1/12 sine 3t. I'll then have to differentiate it again, because this is a second order differential equation. Again, I will do product rule. I will keep the yellow the same, then I'll differentiate this, which will give me -3 sine 3t, and I will then keep the I'll differentiate the yellow to give me 1/4, and I'll keep this one the same, and then I will differentiate this part here. Don't need to use the product rule here, that's just going to be 1/4 cos 3t. And I can simplify this to give me -3/4 t sine 3t, and this will be 2/4, which makes a half cos 3t. Okay, now I've got those, I need to sub it into my differential equation, which is the same as that one, I believe. Yeah, so I'll just use that there. Okay, so subbing it into that, so we've got second derivative plus 9 lots of the first derivative. So the second derivative was this, and then plus 9 lots of the first derivative, so 9/12 is 3/4 t sine 3t, and we then could write that as, well, cancel a half cos 3t, and that is what it should equal, a half cos 3t. So that works. So tick, and you can say that theta is equal to 1/12 t sine 3t is a particular solution. Okay, I might just write here that what we did was we did the second derivative plus the plus 9 lots of theta. Perfect. Okay, next it says hence find the general solution to the differential equation. Okay. Well, we're going to have to first look at the auxiliary equation, which is when we set to the differential equation the left hand side equal to 0. So that was d squared theta over dt squared plus 9 theta needs to equal 0. And we solve that differential equation by substituting in m's, so we get this. And then that tells me that m is equal to plus minus the square root of minus 9, which is equal to plus minus 3i. So now I can write that the general solution is that theta is equal to, now this case where we have only an imaginary part, there's no real, so the real is e to the real part t, in this case 0, so that would be 1, so we don't need to include that, then gets multiplied by a cos of the imaginary part, which is 3, t, plus b sine 3t, and then we can add on the particular integral, which we've already been told, we've already proved works, which is 1/12 t sine 3t. So that is the general solution. Okay, let's go up now to find the next part. It says initially the pendulum makes that angle with the downward vertical, so that tells me that when t equals 0, theta equals pi over 3. And we also know that it's at rest, and when it's at rest it means the first derivative is equal to 0. And that is also at t is equal to 0. Okay, because the angle is not changing at that particular moment because it's just stationary, it's staying still, it's at rest. Okay, so with these two bits of information we can then solve to find our arbitrary constants. So first we can sub in that pi over 3 when t is 0. So when t is 0 we get the cos function gives us 1, so that's a, and the sines will give us 0. So that tells us just a is equal to pi over 3. Now the next part I'm going to have to differentiate to sub in. So differentiating this is going to give me 3a, minus, because cos goes to the minus sign, and it's going to give me plus 3 cos 3b cos 3t, and here we are going to get, we've actually already done that product, haven't we? So let's just pinch it from above here. When we differentiated it we ended up with this. It was a quarter t cos 3t plus a 12th sine 3t. So it was a quarter t cos 3t plus 1/12. And we know this is equal to 0 when t is equal to 0. So only the causes will remain, which gives me 3b. And when t is 0, that will be 0, so that will cancel as well. So this gives me that b is equal to 0. Okay, so our new particular solution will be when a is pi over 3, b is 0, so that cancels, and we also have 1/12 t sine 3t. And the question asks us to find the angle when t was equal to 10. So I'll just sub in 10 here, like this. Go to my calculator and type it in. Okay, great. So I get that theta is equal to minus 0.6618. Just quickly double check what the question actually asked us. It says that the pendulum makes an angle with the downward vertical. Determine, according to the model, the value of alpha to 3 significant figures. Okay, so we'll go with alpha is equal to minus 0.662. And the final part of the question says, given that the true value of alpha is equal to 0.62, evaluate the model. Okay, well that seems to me like a pretty good model. It's pretty close to that. So we can say that this is a good model at t equals 10, because that's the only bit of information that we have. And then it says that the differential equation models the motion of a pendulum as moving with forced harmonic motion. Refine the differential equation so that the motion of the pendulum is simple harmonic motion. Well, that's just when we have a differential equation that's equal to 0. So it's essentially saying this, but without that additional force forcing it, so it's just equal to 0. And that's it. Well, I hope that was useful. If it is, please do like the video and please do share it with other people, and also subscribe. And let me know what you want me to do next. Which modules are you taking for further maths? Which ones do you need the most help in? Bye for now.